Yeah. So what are we going to do today? Today we're going to do interface analysis. Yeah? And probably a lot of you, if you've been exposed to AtomProbe, have already seen some interface analysis like proximity histograms. It's a very, very, very popular one. And usually the way we do that is we create some ISO concentration surfaces or ISO density surface, some kind of ISO surface, and then we base our analysis on this ISO surface. This obviously has one downside, and that is not every object is outlined by an ISO surface, and even if it is, sometimes the ISO surface suffers from the fact that underlying is actually a histogram. Yeah? We have a voxelization, yeah? So we chop our data set into little blocks, and we calculate concentrations of each little block, and then we're sort of outlining, which blocks have the same concentration. And if your histogram bins have very, very few counts in them, because after all we're counting atoms, this histogram can get very noisy, and the resulting isosurfaces can get very noisy. So what we are going to do today is to learn how to outline something that cannot be outlined by an isosurface, and that's actually quite a lot of objects. We've already started yesterday looking into what object dimensionalities we could have. We could have 0D, 1D, 2D, 3D. And today we're going to look into how can we create analysis objects from any topology. And Martin already said it. Things like that are not implemented in any of the commercial software that is out there. And I think one of the main reasons is you need to put in a serious amount of effort in order to be able to code 3D interaction and 3D modeling interaction. But luckily, that is a big industry. 3D modeling is an extremely big industry, and it's growing extremely fast. The reason for that is that, it's the basis of computer graphics. So it's the basis of computer gaming, which is big bucks. It's increasingly the basis of advertising as well. Where there's also a lot of employment and a lot of money. Okay, so what we are going to use today to that end is a program called Blender. And Blender is an open source 3D modeling suite. You can go and download that from blender.org, and I hope all of you have done that and have looked into the fundamentals of how to use Blender, some mesh modeling and so on and so forth, because we are gonna make use of that a lot. And you can see you can do quite funky things with that. If you look at this, model here, you can model stuff really for cinematic purposes, or for 3D printing, or for whatever you like. And we're gonna model for AtomProbe tomography. And the basis of all models and of all modeling software is meshes. There are some exceptions. There's 3D sculpting software like Mudbox, for example. Like Mudbox, Autodesk Mudbox. They are volume based. They generate a mesh based on sculpting volume. This is so-called digital clay. You can also do digital clay work in Blender, by the way. But that's not what we're going to be using. We are exclusively going to be using meshes. And the reason for that is that usually light scattering happens at surfaces. That's not always true. The reason why living things look living is because the light scattering doesn't always happen on the surface. It goes a little bit deeper than the surface. It's called subsurface scattering. But essentially, that's where the light scattering happens. And so, if you want to outline objects in 3D, you model their interfaces, and that's great for us because interface modeling is what we want to do as well. So Blender is not the only program you can use for that. You could use, so this is free and open source, but there's also very, very good paid versions, paid softwares. One of the most popular ones is Autodesk Maya. When you scroll up, you can already see, they're not particularly cheap, but if you're a 3D modeler that doesn't do anything but 3D modeling all day, every day, you might actually benefit from stuff that's in those commercial programs. We're not going to benefit from that really at all, I don't think. Another pretty popular one is Cinema 4D and Houdini. And you can see, here's a very good example. You can see a character for a video game, for example, that's outlined by the mesh, by its mesh, and we are going to do the same today. Okay, so let's jump right into it. So what are the interesting bits? So what can we model that we couldn't model otherwise? Well, very importantly, it's things like grain boundaries. And I think we're just going to start with a very simple grain boundary. And then we can relate our relate our analysis to that grain boundary. So let us all just open a new Blender. I'll just open a new Blender file. No, I don't want to save the Blender file from yesterday. I want a new general Blender file. Save changes, don't save. And when we start out, we always start out with a default cube, a default lamp, and a default camera. So if I press F12 for rendering, it will that setup will give me, well, a render of a cube. So it's a very, very quick start. We're going to get rid of those, and we're going to load in our atom probe data. And the atom probe data we are going to start, I'm just going to clear out all the stuff that we did yesterday. And we are going to start with the very simple grain boundary that we gave you yesterday, which was simple grain boundary, which is this old one that I still had from Sydney. And we're not going to do any reconstruction stuff with that, so this is all just data analysis. Okay, so we can load in the data again. So it's pos equals pos to table, and in this case we need to go to epos. Unfortunately, MATLAB doesn't by default let you pick anything with any of the different file endings that you have here. I find it rather annoying, but anyway. Okay, so that's now loaded in. And the next thing we're going to do is open the range figure. I just need to double click on that one. It will pop up. Just double click on it. And then make sure that we have a variable representing the mass spectrum. So I'll just click anywhere on the base mass spectrum curve, not one of the ranges, but the base mass spectrum curve, and then just pull out the object that this represents by using get current object as the command. And yesterday, I think with the reconstruction workflow, in the beginning, there's also a bit of a shortcut on how to do that programmatically. So just pick the figure, open the figure as visible, and then just pick the mass spectrum out of that. Maybe I'll just do it that way so that it's a little bit easier for all of you to follow. So I'll just and I'll open all of the stuff that I still had open from yesterday, because that's not something we need today. Sorry, I'm probably not the fastest person navigating in Windows. Okay, so we see we have the mass spectrum here, the reference to the mass spectrum. We've got our pos variable in, and let me just plot. species. What species are we going to look at? But yeah, I think yesterday we looked at boron, so boron's a good one. I think there's also carbon and phosphorus at the grain boundary. So maybe let's just add all of them. Carbon. Yep. And what else? What did we have? Phosphorus. Phosphorus. Yeah. And I will actually allocate a variable to that plot. Oh, and we need to load a color scheme. And we need to load an isotopic table. Actually, no, we don't. But let's just do it anyway, because there's no harm in it. Oh, and we need to allocate the ranges. And this time we are going to use the chemical element. So let me just run that and copy all of that. Oh, and let me just copy all of that into the chat. Oh, and I should have just plotted all of the atoms. Okay, and so you can see, yeah, boron's pretty good, phosphorus pretty good. But yeah, we have this very nice grain boundary here, and we want to do a proximity histogram. Obviously, you could argue with this grain boundary, yeah, you might just do a 1D concentration profile with a cylinder that you align to the grain boundary. Yeah, why not? You know, why not? Would do the job. But very often you're going to move to interfaces where this is no longer possible. But we're starting out with something very simple. Starting out with something very simple, and we're going to jump into modeling. So the question is now, how do we get our atom probe data into Blender? This is a very valid question, because obviously Blender doesn't read POS files anymore. Unfortunately, it used to. So as a hint, and this is already a preview to what's going to happen, is that with the Blender 2.8 version, so we used to have a plugin for Blender called Atom Blend, and this was this is a Python plugin for Blender that allowed you to load in your atomprobe.pos and epos files together with range files. I don't remember if we used RNG or RNG, one of the two. And then you got all of your atom probe data in your Blender file. Unfortunately, with Blender 2.8, that broke because they updated a lot, so it was a complete recode essentially of Blender. So what we're doing now is starting next month, I have a student that's going to code an Atom Blend 2.0, which is going to work with the new versions of Blender, and which is also going to make use of a lot of the really cool new stuff that Blender can actually do. Okay, but for now we're going to do the smallest common denominator. We're going to go back to our OBJ files. So OBJ files are great. For that we actually have a convenience function. So you can go OBJ pos to OBJ. And with that you can specify what POS file. So we only have one loaded anyway, so we're going to take that one. We can say which species, and again this is a sort of a list. And I think we're just going to start with boron for now. That was, I think, the best one for well, there was a lot of boron, so we can definitely use the boron. Boron, and we're not going to allocate a file name. It will just pop up with an interface then to export that. And I'm just going to move to simple grain boundary. And I find it really annoying that it doesn't, that I can't just, That it's not like with the Mac where I can just click on another one and I get a name. I don't know. We'll just call it boron.obj. I know that's stupid in a way, but usually you should name it. You should name it after the name of the file that you got it from, or the run number you got it from, because otherwise you're gonna have a lot of boron.objs on your computer, and if you want to search for something, you're gonna have like 50 identical files. 50 identical files popping up, which is really fucking annoying. Anyway, and yeah, I'll just go save. Just go save. And then, just like I showed you yesterday, this is a text file. Yeah? So we can go and open that with a text editor, and you'll see a lot of V's. And if you scroll to the end, what you don't see is you don't see any F's. Yeah, because of course there's no faces per se. We're just exporting vertices. Mind you, this is a text file, so if you want to export 20 million atoms in a text file, that's maybe not a good idea. But usually if you want to outline some interface, then usually, you know, you're going to have a couple of 100,000 atoms max, maybe a million or two. And, you know, storage these days is cheap, and you know, if you really think it's too big a file, then you just delete it afterwards, because it's extremely easy to create it. Anyway, so this is just a list of the atomic vertices, of the atomic locations. What we don't have here is any atom probe specific things. Yeah, so the OBJ doesn't know that this is boron or anything, so we have no way to really save that in an OBJ. There are other file formats where you could do that. For example, PLY. The Stanford polygon format, for example, would have that option. But here, yeah, we can't. And well, the file is called boron.obj, so I guess it's fine. So next thing we're going to do is we're going to go into Blender and load that in. And for now, I'm just going to delete all of the other objects. So pressing A gets you to select all of them. If you call Alt-A, deselects all of them. Pressing A selects all of them. And then just X for deleting, and then deleting everything. You know what? I'm just going to quickly install a plugin, which is going to help a lot. Which is screencast keys, so I can see what keys I'm pressing. And I probably should have done that earlier. Screencast keys. So you can actually fairly easily install plugins in Blender by just going preferences, add-ons, install, downloads, screencast keys, install add-on. Install screencast keys. Install add-on. Okay. Maybe that's not the right time for that now. Anyway, for now, I'm just going to tell you what the keys are, and later on, in the break, I'm going to install screencast keys. Okay, So we're then gonna load in our data, which we do by clicking File, Import Wavefront OBJ, just like yesterday. And I'm going to go into that folder. Is that folder somewhere? Data for isosurface. Is there? No. But that's pretty close. Simple grain boundary. And we've got our Boron OBJ. And if I now click import, you're going to see, oh, they've got rid of them. So it now automatically, it used to be that if you did that, you needed to click to preserve the vertices. But the orientation was wrong. Sorry, I wanted to show you that it doesn't work, but it works now. I find that great. Anyway, import wavefront, Boron OBJ, and just like yesterday, we want Y to be forward and C to be up. And usually what we would need to do is go and click at keep vertex order, so that it loads in all of the vertices that are in our data set. Because otherwise, if I don't click that, traditionally it would drop any vertex that doesn't belong to a triangle, that doesn't belong to a face or a line, some kind of object. Because in 3D animation data sets, what you can have is that you have stray vertices somewhere that don't belong to an object, and it would just go and clean all of this out. In our case, all of our vertices are stray vertices, of course, and we want to preserve them. And now we've got our Boron object here, and you can see we can work with that. You can do, by the way, you can do whatever you want. You can delete vertices, you can fudge your atom probe data any way you want. Obviously, you're not supposed to do that, so don't fudge your data. And if you do, don't tell anyone I told you how to do that. But anyway, you can do anything you want with your data. And what we want is we want to outline a grain boundary. Does everyone have some data in Blender now? Yep. Oh, I see a lot more green ticks than yesterday. That is brilliant. I think the rest is still asleep, probably, right? So yeah, the next thing we want to do is actually create an object that outlines our grain boundary. Yeah? That would be really, really nice. And we do that by going Shift A and then add mesh plane. And now we've got a plane that's actually created wherever our 3D cursor is. I could click here and our no, am I in edit mode? No, I'm in object mode. Why is it not moving the 3D cursor? It will put it wherever the 3D cursor is. So this thing here. And the 3D cursor right now is at the world origin. I could go snap Shift S cursor to world origin, for example, and then it would snap back to the world origin. And the reason for that is that there's two types of coordinate systems in Blender that we have. And one is a global coordinate system, which, as the name suggests, is the same for all objects. And then we have a local coordinate system. The local coordinate system is per object. So each object has an origin in the global coordinate space. And in this case, you can see it's at 0, 0, 0. But if I click on my plane and go grab, I can move it somewhere else. And if I now press N, I can see what the location is. And the location in this case is somewhere, way out. And I can go and move that back to 0, and now it's back to 0. But there's also a local coordinate system, and the local coordinate system is the coordinates of the vertices relative to the origin of the object. Okay, so what we typically want to do is ideally keep the origin of all of our objects the same. So keep it at the world origin. So what we are going to do is we are going to move the vertices, and we're not going to move the object. This is not 100% necessary, because we can also move the object as a whole, and when we export it, it's kind of made sure that the vertex allocations are relative to the world origin and not relative to the object origin. But if you export objects to other software, and re-import and so on and so forth, then that's not always guaranteed. So I think it's good practice to keep the object origin at the world origin, but it's not 100% necessary. Yeah. So okay, so let's then go and move our grain boundary onto the object. Our grain boundary model, which now obviously is not a particularly good model. It's a plane just anywhere in the world, in the world space. And how can we do that? Well, we move from object mode. So in object mode, if I go G for grab, I'll move the entire object. But we don't want to move the entire object. We want to go into edit mode, and we can also do that using the tab key. And now you can see, okay, we have the vertices of the object. Yeah, now we are moving the vertices, and that's actually what we want to do. And in this case, it's actually not particularly complicated. So if we look to the side, we can press G for grab and just move it somewhere where the object is. So that's actually fairly simple. And then press scale to scale it up to, I don't know, so that it covers the entire object. And preferably do that in orthogonal mode, so that you actually get a good view on your object. And in this case, I'll just also press R for rotate and rotate the whole plane so that it outlines the grain boundary pretty okay. And then maybe look again at 90 degrees to that. And rotate the whole thing again. And, well, we have a pretty good model for our grain boundary now. Do we? I mean, it's sort of a little bit larger than the data set. It's, I don't know, it's obviously very simple because only 4 vertices. But it depends on what you want to do. So if you want to do a proxygram to your grain boundary, yeah, that would be enough. That would actually do the job. But if you want to go and calculate any properties that are relative to the grain boundary area, obviously it's not a particularly good measure of the grain boundary area that we calculate. So if we calculate what the area is of that plane, it's obviously not the area of the grain boundary that we captured. Yeah. So we need to sort of cut it down to size a little bit. Yeah. And also maybe this is just us looking at it, and creating the grain boundary. So we don't know if that's the best fit ever. Yeah, maybe locally it needs to be fit a bit better. But this is a starting point. Yeah. So the question is now, how do we refine that? How do we make a really nice grain boundary model out of it? And the first thing is to we need to know where the boundary of our object is. Yeah? So we need to know what the boundary of our data set is, and we've already talked about that yesterday. The best way to do that is if you already have a co-reconstructed model with nice mesh topology and everything. But maybe you have a POS file, maybe you don't want to do your own reconstruction. Yeah, and in this case, we'll just create it off of our data here. Yeah? And this is what we did yesterday already with the sampled alpha hull command. In this case, I think the POS file is only about 1 million atoms anyway, so we can maybe use all of that million atoms to create our sampled alpha hull. Yeah. And just run that command. And let me just copy that over into the chat again. Shouldn't take too long to calculate a alpha hull from 1 million points. Yeah, you can see we've got a pretty close outline. Got a pretty close outline of our data set. The mesh isn't pretty, but I mean, where the grain boundary is in the middle, it's kind of alright. So usually those alpha hull meshes, they're kind of alright if your data density is high enough. If you've got some reconstructions of I don't know, something ugly like nanoparticles or whatever, you might have a low data density somewhere, and the mesh then gets pretty ugly as well. But if you have something that's pretty solid, then you get on the sides, you get pretty good mesh density. It's usually the corners that are a little bit more critical, but we have a pretty nice mesh. So let's just export that mesh again. So we can just do that by patch to obj, and we are going to export the hull, and we are just going to export it to the simple grain boundary folder, and we'll call it hull. Yeah, again, usually I would call it R04_11350_ hull or something like that, so that recon version 01 hull or whatever, yeah, so that you always know which data belongs together. Otherwise you can have a whole bunch of hulls that you never know, without looking into it, you never know which data set it belongs to. So okay, so we've got our patch to obj. And the good thing is also it will tell you what your dataset volume is. In case you didn't know what your dataset volume is, maybe you want to know, some volume density, and you can just calculate it from there. But that's the volume of your dataset domain. So if you've got something where the volume is not fully filled with atoms, that's maybe not a good measurement of the volume that you captured with the atom probe. Okay, and the next thing we're going to do is, I think Martin gave you a link to a program called Instant Meshes. Did you do that, Martin? I think that was part of the package, right? So if we have an ugly mesh, we can sometimes make pretty meshes from ugly meshes. And a program that we use for that is Instant Meshes. You can just go and download that if you need to. Oh no, that's something else. Yeah. So Instant Meshes. And what Instant Meshes does is essentially it calculates the principal curvatures of your mesh, or okay, it didn't include the link, but I can just put it in. It's a quick download. It's a quick download that you should be able to do in a couple of seconds. And it produces weighted distance fields, curvature fields on the surface, and just estimates of what a good remesh would look like. In this case, with quadrilaterals or triangles, you can pick that, and it will just know how to do that. And that's something that I already did yesterday. Anyway, we're gonna load it in a different one now. We're gonna load in the one we're working with currently. So I'm gonna load in the hull.obj. You can, say, okay, I want triangles, I want quads, and open mesh, hull.obj, open. Does it want me to kick out the old mesh first? I'll just close that. Oh great, now I forgot where I've saved Instant Meshes. Maybe it's in the downloads. Okay, let me download Instant Meshes, just like you did just now. You can get it as a Blender plugin now as well, I think. Microsoft Windows. Save. And now it should be in the downloads folder. Okay. So yeah, it's a very quick download. Open instant meshes. Open hull.obj. Why can it not open hull.obj? Let's look into some troubleshooting of OBJs. Maybe during export there's something that didn't look quite right. So open with editor. And so one thing that can happen is that it's not happy with how the objects are defined in there. Object mesh 1, that looks fine. So maybe something that's unfinished. I have actually no idea. It's like it's a very nice looking OBJ file, so I have no idea why I can't load it. Weird. Anyway, so we're not gonna remesh it for now. Maybe we can troubleshoot that in the break. But you can usually use instant meshes to remesh your hull. But now we're just gonna load it in as is. So import wavefront obj, hull.obj.
Peter?
Yeah.
Did you load the hull in the in Blender first before using instant message?
No, I've loaded it in now.
Okay, it sometimes solves the issue.
Okay. Anyway, so now we actually have a measure. So we have an object that tells us where our data set ends. So you can see it's sort of semi nice looking mesh here, and here we've got our object. And yeah, so our object only actually. So I'm gonna make that semi-transparent. So I can go to the object properties, visibility. Oh, sorry, not visibility. Viewport display, and I want to display it as a wire object. Want to display the name on top and axis wireframe in. You can define a lot of things here. Anyway, so we displayed it just as a wireframe so that we can see all other stuff that we have in there. Okay, so now next step is to subdivide our object here. So I go back into edit mode for this object, and now I want to create a lot more vertices than I had before. So this is called subdividing. Yeah, and subdividing used to be W. I don't know why they've changed it. That is really annoying. Sorry, I have to look up what subdivision is now. And I think it was on edge, right? Subdivide, yeah. Subdivide, and we are going to subdivide. I don't know how many subdivisions do we want to have. How fine do we want the model to be? What is a good choice for model fineness? I don't know. But if I subdivide, I probably should have looked up how large I made the entire object. So this object is now, what's its size? X and Y, it's 40 nanometers in X and Y. 40 nanometers. So if I divide it into 10, then we have 4 nanometer steps. So if I go in and we have a 9-fold divide, that's 4 nanometer steps. And if it's a good choice or not, again, I don't know. I don't know how dense your data is, how many atoms you have there. And I think I wrote a paper. I wrote a paper once that goes through all of the statistics and everything. But you're not going to worry about that. Okay, so your mesh is loaded fine. That's good. So you can later show us how beautiful your meshes are. Okay, so what step size is a good step size is kind of like the same with the same thing we talked about yesterday with the voxelization. There is no good choice. If you make it very small, you're gonna have low statistics. If you make it very large, you're gonna have low resolution. For now, also we still have something that's just a plane. Yeah. So if you have a plane or something that just has one curvature, you can actually have even distances between the mesh points. If you have something that's curved in 3D, that's in principle not possible. You cannot have something curved in 3D where you have even distance between the mesh points. So this is also something you need to be aware of. Yeah, so these nice square looking things, we're not going to work with something that's very curved in 3D. Okay, so what are we going to do next? The next thing we're going to do is we are going to delete all of the mesh points that are outside of our data domain, because they don't make any sense. They don't make any sense. And I'm just going to do that using this circle select tool. So you can go C for circle, select tool, and then I can go and mark everything that's outside. All of our vertices that are outside, even those that are barely outside. Yeah. There's one more. Oh no! I lost all the other ones. So C for circle select again. And then select that one again. And that's that. And then hit X to delete all of those vertices. And now we've only got the vertices left that are inside. Maybe some of those that were barely outside we might have kept. Yeah. But yeah. I think this is just a basic introduction to modeling. A basic introduction to modeling. And you can see that, you might have made a finer mesh. With a finer mesh, it might have worked a little bit better. But this is now our initial starting point, and we are going to go and improve upon that. So now you might think, why don't you just make an extremely fine mesh? And the reason for that is making a mesh finer programmatically is always easier than making a mesh coarser programmatically. This may be a little bit counterintuitive because usually, finer, you think you have more information, so it's easier to go out. But topology, when it comes to meshes, topology is king, and topology is always a difficult bit. Of course, if you don't do any mapping on it, because later we're going to get into mapping, and then the distance between the mesh points is going to become very, very important. Okay, and so the next step that we're going to do is create a topology with that grain boundary that we can actually fit to the data domain. Yeah, because what we're going to do is we're going to move all of our outer vertices actually onto the boundary, yeah, so that our grain boundary actually is tied with the hull. You can do all of that manually, by the way, yeah, but I will show you how to do it programmatically, because that just might save you a fair bit of time. Yeah. So the first thing I'm going to do is I'm going to switch all of those things off. Here we've got one vertex that's sort of very lonely here. And what we are now doing is creating a mesh topology that we can fit to the boundary much easier. And the first thing we're going to do is hit F for face. We're going to mark 3 vertices and hit F to create a face there. 1, 2, 3. Hit F to create a face. 1, 2, 3. Oops. That was caps lock. Oh, no, not C. F for face. F for face. Oh, yeah, we've got a vertex here. F for face. Vertex here. F for face. That's, by the way, not something you absolutely have to do, but it just will make your mesh topology nicer afterwards. So again, if you do proximity, if you measure concentration towards the interface lexes, proxygrams, and it's not as big of a problem. If you want to do stuff laterally on it, you need to make sure that you've got a good mesh topology and a good and a nice looking mesh with even distribution. Okay, so now we've got something that, you know, doesn't quite look like the intersection should look like, but you know, it's kind of alright. So what can we do on top of that? You know, we could go and just
Peter?
Yeah.
Just quick. Could you say again how you can add some faces?
So if you want to add faces, you just mark the vertices that you want to belong to that face. Yeah. So let me just switch off the hull again. So if I want a face between these three, yeah, I just click on them, hold Shift pressed, and then I press F, and then it creates a face. And you can do that with 2, 3, or 4 vertices or more vertices. Blender actually supports polygons. I highly discourage you from creating polygons because then the plane is really badly defined. That's something for people that want to make movies, not for people that want to do data analysis. So who's made it that far is us, at least some pages. Is everyone on the same page as me? Does everyone have a grain boundary? Okay, I see some green, not just green from Erlangen. That's good. Okay, so one thing you have to learn the hard way is topology doesn't come for free. Yeah? So all of those mesh triangle relationships and so on and so forth, we can pretty much only easily create them by hand. Yeah? If I had an algorithm that creates mesh topology just out of thin air, I would be rich, super rich. Yeah? So unfortunately, something like that doesn't exist, and it's not trivial to make something like that. I have some papers out there with all kinds of tricks of how to make those meshes, but in the end it turned out that, you know, a bit of manual labor was always the most reliable and pretty much quickest way, I have to say. Okay, so let me switch on the hull again, and the one thing I'm going to do now is by just looking head on to my, you always have to remember, if you move a vertex, it will move perpendicular to your view plane. Yeah? So if I look this way, it will move up and down, which is not great for our grain boundary. If I look head-on from here, it will move in, you know, my head-on plane. And we'll move stuff later on anyway, programmatically as well. And so what I'm going to do is just make the whole thing a little bit nicer looking. By just clicking on them and use G for grab. But we're going to use an algorithm later on that's actually going to make sure that our vertices are a little bit more even distributed. So now you can see if you just want to calculate an interfacial access, that's probably not too bad an approximation of what the area is your grain boundary takes up in the data set. It's not perfect, you know. If I go and click on the hull and maybe make it appear in full swing, we can see that the vertices are not exactly on the boundary, so we're missing a little bit of area, but we're not missing that much area. Maybe a little bit, but not much. Okay. And so what we're going to do now, we're going to go back into MATLAB and use a couple of funky algorithms to make that a bit of a better approximation of where our grain boundary is. Yeah? But there might always be a little bit of manual labor involved. Okay, and how do we re-import that? Just like I showed you yesterday, click on File, Export Wavefront OBJ. We want our selection only, and we want Y to be forward and Z to be up, and we want triangulated faces, no materials, no normals, and no UVs. And later on, we're also going to use polygon groups, but that's not something we're doing right now. Right now, we're only going to work with triangulated faces and our selection here, and a scale of 1, obviously. So we're going to go, and I probably should save it here. So I'm gonna call it grain boundary raw or grain boundary initial, or let's call it grain boundary underscore 1, and then we'll just iterate. Oh, I've got the caps lock on. That's why I was there. Grain boundary 1, and then we'll just iterate over this number, and the highest number is always the best. So we'll export the OBJ. We'll export the OBJ, and then we'll load it back into MATLAB. And we do that with the OBJ to OBJ equals OBJ to patch command. You've learned about that one yesterday already. And here we go with grain boundary 1, and we'll turn it into a patch again. So fv.faces and fv.vertices from the object. The question was, how do we do the grabbing again? G for grab. Yeah. So sorry, in the break I'm gonna install the screencast keys successfully so that you can always see what buttons I'm pressing and what mouse actions I'm doing and so on and so forth. I should have done that beforehand. Sorry about that. And now we're back in business in MATLAB, where we have our hull here, and I can just go and plot that patch. Face alpha 0.6. It's not a deconstructed object. It's our grain boundary, and now it should appear in here, and I probably should have also given it a different color so it's a little bit easier to see. But it's here, and it's sitting where it's supposed to sit. And we could already do a proxygram based on that, but we're not doing that because in the first session we are just going through how to model nice grain boundaries. So the first question is now then, well, how do I get let me just close that up so that we only have the remaining few figures remaining. How do I get the grain boundary to sit perfectly on our our atomic positions? And the algorithm for that I've published a while ago. Well, there's a couple of ways you can do that. And we have actually published an algorithm that is based on ray tracing 2-3 years ago together with computer graphics people here in Erlangen. But unfortunately, I don't have a distributable version of that algorithm. So we have developed an algorithm here that is essentially as simple as using an isosurface to create a grain boundary, but that one would really need to be recoded to be easily usable. But what we can do is we can take our initial model here, and we can snap the vertices to our atomic positions. And what I mean by that is a very simple algorithm, which is called the distance to center of mass algorithm. And it's actually a very simple thought. So let's say you've got atomic positions. So your atoms are sitting, like your segregated atoms are sitting here. You might have a couple of stray atoms everywhere, but you have your grain boundary or your interface, and you've got segregated atoms to there. Obviously, isosurface not a particularly good choice because you get little chunks everywhere. But we might already have our grain boundary as we have it here, and its outline is kind of right. Let's just say it's a little bit off. So it's this might be our. Obviously just a 2D approximation. This might be our grain boundary. We've modeled it, and we've modeled it kind of alright, but not perfect. What we can do is actually we can move the vertices to the center, to the barycenter, to the center of mass of. And why can I? Let's try. Can I? No. Better. Okay. So So I can just draw a circle of a whatever size, of radius r around my vertex, and just look at the atomic positions. Look at the atomic positions of a certain type of atom. I can pick what type of atom that is. And in this case, this atom would be inside the circle, this atom would be in the circle, and I'm seeing my choice of color is stupid. So this atom would be inside, this atom would be inside, this atom would be inside, this atom, this atom, this atom. And now I'm just calculating what the center of mass is of these atoms. I've got 5 here, 2 here. So let's say the center of mass would then probably be somewhere around here. Somewhere around here. And what I'm then doing is I'm going to move the vertex, not to the center of mass, because you can imagine, if you've got a lot of atoms here and a lot of atoms here, then this one would move here, this one would move here, and then they would sit on top of each other. So that's not a good way of doing that. But what we're going to do is we're going to use the surface normal. So the surface normal of our atoms, of our vertices. So the surface normal, I'm going to show you in a second where you can find what the surface normals are. So I'm going to move it along the surface normal to that point. So I'm going to move it here. I'm not going to move it straight on the barycenter, but I'm going to move it to here. And I'm going to do that with all of the vertices. And so my next iteration is going to sit probably somewhere here. So it's a much better outline than it was before. And if I do that one more time, then I think it's probably going to sit on. So it's probably going to sit on here pretty solid. So this will converge if I do especially if I have a good model. So this would be sure. This would be first, and this would be second decom step. Of course, if my initial model is already pretty good, then probably one step is going to be good enough. This thing obviously has one downside, and that is at some point your data is just going to end. So you're going to have your data set hull. The data is going to end somewhere here. So for all of the vertices very close to the end, they're always going to be slightly pulled inwards, because obviously there is no atoms outside. So we might need to deal with that one afterwards. So we might need to adjust something there. But the better my initial guess is. On the first step, by the way, it's always going to move on the normal. So if I have a really good initial idea of where the grain boundary sits, one step is probably going to be enough anyway. So do good modeling, then you will get good quality. Results. And maybe one day we're going to be able to give you our super duper ray tracing algorithm, so you can outline your grain boundaries with just a click. Okay, so let's jump back into the whole algorithm part. So the question is now, I hope the mesh is not going to be so ugly that we're going to get problems with our algorithm later. So the hull, but for now it doesn't matter. So the thing what we're going to do is called, I'm just going to call it FV1 so that we're doing it non-destructive and we remember what's what. Is a patch snap to atomic positions. So this is what the decom algorithm is called in what the function for the decom algorithm is called in our toolbox. And all we need is our interface FV and the atomic positions we want to snap to. And in our case, that's pos dot atom equals boron. So we want to have the boron atoms. and we want to have a decom radius of, I don't know, what radius do we want to have? I mean, the stronger the segregation is, the clearer it's going to snap to anyway. So I don't know, maybe we'll use 5, 10 nanometers. I don't know, what would be a good, I don't know, we'll try 5. And that went fairly quickly. And now I'm just going to go and plot my my boron atoms. I'm just gonna stick with the boron atoms, and I am going to plot the patch of FV1. That's our interface now, and I'm just going to give them a name, and I'm going to create an array of those patches, just so that I can go and delete them programmatically later, and I don't need to click on stuff all the time because it becomes annoying after a while. And maybe I'll give it a different color. 111 would be white, so I don't know. I don't know what color RG. What color do I get if I red and blue? Oh, we're gonna find out. I'm not good with colors. All right. And oh, I would have to. I would have needed to go sky to plot both data species, and I want to plot all of them. I want to plot all of them, and hold on so that we plot into that, and we will plot that stuff. And now you can see, yeah, that is already a pretty good outline of where our grain boundary is, and it's pretty close to what we had before, but it now takes the subtle, the really subtle bends we have in our grain boundary. It really takes that into account a bit more. Yeah. Of course, this is a very, very simple grain boundary, yeah, so outlining it manually wasn't actually that hard. Yeah. But I think this is a pretty satisfactory result for now. Of course, we can try what happens if we do that in another iteration. Yeah. So let's just go FV2. So we'll snap the and create that patch from FV2 and maybe give that a different color. This is now blue. And you can see we're pretty much converged. There isn't very much of a difference anymore between the first and the second iteration. So it sits on our grain boundary pretty solidly, and there isn't going to be, you know, you can calculate what the difference is between the first and the second iteration, but it wouldn't be much. By the way, very similar algorithms are used in finite element analysis to create finite element meshes, and they usually use something called energy criteria for convergence. So they just say that the square of the you sum up the square of the displacements of the vertices during the algorithm steps, and if the square of the displacement falls below a certain fraction of the first step, then you call it converged, usually about 5%. In our case, it's usually, if your grain boundary model you started with is pretty good, then, well, there isn't that much need. Let me just copy all of that into the chat. And stop me if this is going too fast. Yeah? Okay, so we're pretty happy because we have a grain boundary that now actually sits on our. We have a grain boundary model that sits on our grain boundary pretty okay. Yeah, so we again proxygram already, no problem. Interfacial access calculation, no problem. But the question is now, does it really go all the way to the boundary? And the answer is, well, no, because we kind of made sure it doesn't. Yeah, we kind of made sure it doesn't go beyond the boundary because that would be bad. But we wanted to go exactly to the boundary. Yeah? And for that, let me just delete everything, all of the patches. So this was just, you know, deleting them out of the plot so that they're all gone. And because the next thing we want to do is call something called stretch to boundary. Yeah, so we're gonna go FV3 now. Yeah, because I'm just making sure that at each step everything is documented. FV3 is patch, and there should be a snap to atom position, split connect is stretch to hull. Yeah, so stretch to hull. And what do we need? Well, we need our patch, which was FV2, and we need a boundary, and the boundary is the hull. Yeah. And I really hope that the ugly hull mesh is not going to give us problems. Yeah? And this is one of the reasons why we usually try to get a really nice boundary mesh, so that, you know, any like tiny triangles that happen to be tilted in a weird way, something like that doesn't give us issues. Yeah. But I guess we're going to see. And let's just plot that patch. And since I've deleted all of the patches, I guess we can start at patch 1 again. Now, our FV3. And yeah, we didn't get any problems, so that is all good. So now if I add the hull to that, yeah. So our patch 2 is now our hull that we are plotting in. And maybe again a bit of a different color. And maybe we'll make that one very, very transparent. Yeah, so that it's very see-through. You can see what we're doing. And now you can see that our grain boundary goes all the way to the boundary. It goes all the way to the boundary. The question is, of course, you all love algorithms. So the question is, what algorithm do we have to do that? And that's actually a very simple one. It's a very, very simple one. So essentially, if you look at these triangles here, I'll just make a very, very simple grain boundary, and we'll have something. And this is our hull. What it does is essentially it goes and looks up what the line elements are here. Oops, that's not what I wanted. The line elements are here, and then it will create a vector that goes straight out from the line elements. Yeah? So it will find out which line elements constitute the boundary, yeah? And then create vectors that are going out in this direction. And if you look from the side, so this is now from the top, and if you look from the side, it will just look up what the surface normals are. What color do we use for the surface normals? So we'll just create the surface normals and make sure that these vectors are normal to the surface normal of the adjacent triangles. There's a little bit of math involved here. I'm not going to bother you in detail, but you can look into the algorithm. It was a bit of work to write that one, but that's fine. It's been written a long time ago. Anyway, and it then goes and along this vector finds the intersection with, well, any mesh. You can use it with any mesh, but usually we use a boundary, some kind of hull. But you could stretch any mesh to any other mesh. Doesn't really matter. But usually we use boundaries, and then it just moves it out there. And this is essentially all there is to it. Obviously, the finer details are that, you know, what happens with the triangles and so on and so forth. But I do not have to. Oh, that was a stupid sketch. I do not have to bother you with that. Yeah. All you have to understand is that that's actually a fairly simple algorithm. Yeah, it's a fairly simple algorithm. Yeah. Okay, so now we have a fairly nice grain boundary that we've outlined. The only thing that's maybe a little bit uncool. Let me just plot the grain boundary separately in a new figure.
You gotta switch your screen.
Oh, thank you. I will never remember to do that. But that's what I have you people for. Okay, so so what did I want to do? I patch, create the patch. The last one that we have was called FV3. And let's make the axis equal. Oh, we could APT-fy the axis now, but it doesn't matter right now. Why not? Why not? Why not APT-fy the axis? So the only thing that's maybe still a little bit uncool is, well, we have some triangles that are like nice quads, and we have that represent quads, and then we have some triangles that's sort of elongated. So we have this area that sort of still represents what we had earlier with our initial try. And then we had all of the vertices that have been stretched to the boundary, moved by me manually, and so on and so forth. How do we do that? Well, there's another algorithm. You could do that by hand. You could go and move them by hand and distribute them however you want them to. And sometimes, that's actually not a bad idea. And there's a lot of tools actually in Blender that allow you to do stuff like that really efficiently. So you can move vertices around, even if it's hundreds or thousands of vertices. There's a lot of tools to do that. In the last 15 minutes, we're not going to have the time to look into that, but we can also do that using algorithms. And the algorithm that we are going to use for that is called a centroidal Voronoi tessellation. If you have ever wondered why robots move in those really robot-y ways, the reason for that is exactly that algorithm, a centroidal Voronoi tessellation. And hopefully, after I explain the algorithm to you, you will understand why robots move the way they move. So just imagine you have a certain amount of points in a domain. So we have a domain. And we just threw in a bunch of points. Randomly threw in a bunch of points. Some of them close together, some of them far apart. And we want to have those points be fairly evenly distributed, either locally evenly or globally evenly. How would we do that? And we do that using this centroidal Voronoi tessellation. And maybe I should have drawn 3 points, otherwise it will take forever for me to draw those points. But essentially how the algorithm works by creating a triangulation, a Delaunay triangulation, and its geometric dual, which is the Voronoi tessellation. And what the Voronoi tessellation represents is the area around the point that is closer to that point than to any other point. And I'll just draw it for this point here, because here this is where the interesting bit is. There's the intersections between individual lines here actually gives you maybe my Delaunay triangulation was already not that great, but I hope you all understand I'm already at the next one. That was stupid. I'm already around the next one. So you'll have that here, you'll have that here, and maybe there would be a point sitting up there. And so then the next step that we do is we move that point. To the center, to the center of gravity, of that domain here, of that Voronoi cell. Obviously, my sketch was a bit off, so I've moved it outside of the center, but I think you get the idea. So if you have 2 points that are close to each other, they are going to drift apart. If you have 2 points that are very far apart and have points that are close to each other here, then they're gonna get closer together. Yeah? And you can do that with a whole number of iterations, and then you get a very even distribution of points. So why is that relevant to robot movement? Yeah? Because a robot very often needs to move in a domain, yeah? And whatever that domain, if it's a vacuum robot, the domain is your living room, yeah? Or the map it has of your entire flat. Yeah? And what it then does is it takes that map, randomly throws in points, yeah, and uses these algorithms, Lloyd's algorithm, central Voronoi tessellation, it's also called Lloyd's algorithm very often, to distribute those points in space, and then moves from point to point. Yeah? And this is why the robots move that way, because they move from point to point in their domain. And I'm pretty sure if I look online, I will find a pretty nice animation of what that looks like. Lloyd's algorithm. So if you just Google Lloyd's algorithm and find some videos. Yeah.
What's it like to learn math on brilliant.org?
Oh, come on.
Hands-on to help you learn by doing.
Peter, dein Bildschirm.
Thank you. Yeah, so you can see this is Lloyd's algorithm at work, and you can see it tends to converge pretty quickly. And maybe they should have used something that is uglier in the beginning. Yeah. Anyway, this is what Lloyd's algorithm is. Yeah, you can find some pretty nice videos about that. With the only subtlety that we have here is that we're in non-Euclidean space. Yeah. So generally our interfaces are going to be curved somewhere in space. Yeah? So I had to come up with a Lloyd's algorithm that works in non-Euclidean space, so in curved space, but I'm not going to go into detail about how that works. That would really go beyond the 10 minutes we still have left. The only thing you have to worry about is, well, you don't have to worry about anything because I've made it work in curved space as well. So it doesn't matter if your grain boundary is perfectly flat or not perfectly flat. You can still use that. And so how do we apply that? Well, we now create our patch FV4 is patch centroidal Voronoi tessellation. Lloyd's algorithm and centroidal Voronoi tessellation is the same. Yeah? And in this case, our original mesh is FV3. How many steps do we want to do? Well, let's start with 1. And then at the end, you will find something called angle limit. Yeah? And the reason why there is something called angle limit is because we're not going to do it on a fixed domain because it doesn't make all that much sense. So if you imagine it's not that applicable for our problem right now because we're outlining something to the entire boundary, yeah? to the dataset boundary. But just imagine you had a rectangular region of interest, yeah, that you're working on, and your interface that you've created goes all the way to the boundary of the rectangular interface. What the algorithm would like to do is round out that rectangular interface, yeah, to make everything round. That's why I've put in an angle limit that if two vertices have an angle between them that is smaller than that angle limit, these vertices are going to be pinned. Yeah, we're not going to move those vertices. Yeah, so if you have any corners, they're going to be preserved. Obviously here we don't have any sharp corners because we're going out to the dataset hull, so the angle limit doesn't really matter. Yeah? But usually, if something has an angle of smaller than 60 degrees from flat, then probably we want to pin the corner. In this case, it's not really applicable, yeah, but sometimes we want to do that. Okay, so it then performs that centroidal Voronoi tessellation step. And where do we have the... well, I'll just plot it in here so that you can see the difference. So we'll go patch FV4, and again we are going to change the color so that we can see what it did. And maybe I should not have, that wasn't maybe the greatest idea to plot it this way. So let's just delete all of those and plot it in again. And now you can see we already have a much more even vertex distribution. Yeah? And this is going to be, again, this is only going to be important if we do lateral analysis. But you can already see that there is some issues that we have, and this is something I call trapped vertices. So here you've got something that kind of looks like a quadrilateral, but you have one vertex here that, in your Lloyd's algorithm is always going to be trapped topologically by the neighboring vertices. Yeah? So if that's something that bothers you, you might go back into Blender and just delete that vertex and just make that just get rid of that topologically trapped vertex. It can be an issue. It isn't necessarily an issue. Okay, so what happens if we run 2 CVT steps? Yeah, you can see it didn't change all that much anymore, so it converged really quickly. Yeah. I think as a last thing, we might want to plot that on top of our nice atoms to see if everything is if something is shifted, because I mean we are shifting vertices. Yeah, so these vertices are not necessarily moving where our atoms outline the grain boundary. Yeah, so we might need to snap them back onto the dataset boundary, and we might need to snap them back a little bit onto the atoms. And this is going to happen stronger the more curved your object is. So if you've got a very, very curved object, you might need to resnap it. Now we have got a very flat object, so we are not going to need to do that very much. Yeah? But yeah, let's just go and plot our boron atoms again, and plot our patch object on top of that. And now you can see we've got a fairly nice grain boundary model. Okay, and now we took an hour and a half to model a grain boundary, but I can assure you, if you've got any amount of experience doing that, it will usually take you like 5 minutes to model a grain boundary, especially one like that. It goes very quick. Yeah, go into Blender, rough outline, cookie cutter, punch it out, then move back into MATLAB, stretch it to the boundary. Redistribute the vertices if you need to. If you want to do snap the vertices to the atomic positions. If you've got some segregation where you can do that. Sometimes you don't have segregation or not a lot of segregation. Then you're probably bound to doing most of it manually. So the snapping to the atoms only works if you've got enough atoms to do that. Sometimes you don't. Then you might need to go back and manually edit where the boundary sits, because one vertex might have been pulled up to somewhere in space. Yeah. So so there might be some manual work involved, but in the end, if it looks really good, then probably it is really good. Yeah. And this would be the basis then of your analysis. Yeah. Okay, and with that, I think we're pretty much at the end of the first session. Questions? Do you have questions? How many of you made it to a reasonably good-looking grain boundary model? One person. It's better than nothing. I think Martina's green tick was still there from earlier. Okay, you might just need a little bit of practice, yeah. But with a little bit of 3D modeling practice, you can create really nice interfaces. I mean, one of our PhD students here, Andy Ferner, for example, he had some extremely complex grain boundaries or interfaces, stacking faults that he was outlining using some hand modeling and some other algorithms, and you can get to some really cool models of something, where you can really pull out knowledge about your data that you can't pull out any other way. You can't use an isosurface for that. The grain boundary, you wouldn't be able to do an isosurface for that. And stacking faults. This was just modeling of 2D objects, but of course you can do the same thing with 1D objects. So if I go back into Blender, I'll just add a new mesh and just pull it off somewhere into the middle of nowhere, just because I want to show you some stuff. it can do the same thing, and we have algorithms also in there to deal with. And in this case, I'm just going to delete all of the vertices. Sorry, that was stupid. I'm going to Alt merge all the vertices. Merge. Why have they changed? Merge all the vertices at the center, and then I can do the same thing with line objects. Yeah? This would obviously be maybe another tutorial to do, but yeah, you can outline these locations. Yeah? You can outline these locations, triple lines, whatever you like. Yeah, or sometimes with our cluster code. Our cluster code also outputs the Berry center of your individual clusters, so you can do you can do all of the analysis with respect to just clusters. Yeah, so you can have a proxygram to clusters, and it's something we have in some papers. Yep, I will just put all of the code into the chat window. Yeah, so all of the code is in the chat window now. Okay, good. With that, we're gonna stop the morning session. And the next session is on proxygrams and ND analysis. So we're going to show you how to do proxygrams based on the objects that we create. So if you take the half an hour and create your own analysis object, that would be great. Otherwise, or maybe we can just send out the object to you so that you can. Yeah, I'll just save the patch that I've created and send it to all of you as an OBJ, so that you can catch up if you haven't made it so far. Okay, so we'll go patch. Oh no, there's a lot of patch commands. Patch to OBJ, and now I want to export FV4 because that's our good final one. Simple grain boundary, and that's why we call it grain boundary X, and this would now be grain boundary 2. Yeah. So, which is much nicer than grain boundary 1. And save it. And Martin, can you just send it out per email to everyone? I mean, this is an extremely small file. This is just, I don't know, a couple of kilobytes max. Probably not even. I mean, it's just a very small text file, 4 kilobytes. So shouldn't be a big issue to all of you. And by the way, yeah, you can go and take those objects and you can 3D print them and do whatever funky thing you want to do. Obviously, just 3D printing a disk isn't all that exciting, but if you have one of those really funky bent grain boundaries that go off into all kinds of directions, it might be worth to 3D print them and put them on your desk or show them to people. Yeah, do cool stuff with it. Okay, so I'm now going to stop the recording, and you can keep asking questions if you want to.